So just to briefly explain the cold roll forming process, it is passing coil or flat strip material in coil form through a series of tandem roll forming rolls, as you can see on the left hand side of the screen. Each forming station imparts a unique or particular shape onto the profile, and it's progressively formed to end up with the finished product out of the final roll station. It's then cut to length. If there are any additional processes, then these are done afterwards. And what you can see on the right hand side of the screen are a variety of cold roll form products that we've developed and designed over the years. Cold roll forming produces products with a consistent cross section in a constant gauge. It can be used to process materials from really 0.4, 0.5 millimeters in thickness up to about 8 millimeters in thickness. And we cold roll form a variety of materials, steels, copper, stainless steel, pretty much any formable material, but the majority would be steel or stainless steel. So why do we need to simulate? What do we need to analyze? Well, the main thing that we started looking at a few years ago was analysis of the tooling design process. And I'll give a case study about that. But we use simulation to optimize tooling design so that we can have fewer prototypes. Obviously, every time we develop a prototype for a particular profile, it can be very costly and time consuming. And also when we produce the tooling, we quite often have to do modifications or rework particular parts of the tooling process in order to achieve the correct profile at the end. So we're using simulation now to improve the tooling design process. So the packages that we use at the Handley Group, there are two of them. The first being a vertical solution. So this is a kind of a wrap around the MSc Mark and Mentat pre and post processor and solver. This has been developed by a company called DataM, and the software is called Copra FEA. And what it does is it provides the tool designer, the roll tool designer, with an interface with which to very quickly translate the tooling geometry and generate a mesh for the strip into the Mark solver. And as you can see on the right hand side, will show how a particular profile is being formed. Okay, there's also fairly simple pre and post processor options to analyze the data and to set up the material properties, if you like, and the mesh geometries. The second package is MSc Mark and Mentat, and we also have Patran, and we use this software to do pre and post rolling analysis. What you can see again on the right hand side of the screen is now the cutting of the profile that you saw being formed with the Copra software. The benefit of having both packages using the same software is that we can take the pre-state stresses from the roll forming process and put these into a post rolling operation, and we can look at those products within a system. So the case study that I'm going to talk about is the cold roll forming process, and just to put a bit more kind of emphasis on why we got involved with simulation. Roll tooling design is generally regarded as a black art. It's something which requires a significant amount of knowledge and experience, and the designers will learn or gain this experience through, if you like, the number of successful designs that they've produced in the past, but probably also quite a few that have gone wrong. Now, there are a number of questions that the designer will ask during the forming of a new design process, and many considerations such as how many forming stations to use, how much forming to do between each station, understanding how the material might behave during each forming operation, and then to look at overcoming typical roll forming problems where the product might twist or bend or spring back, as we call it, end flare, or where we're trying to bend without an inner forming die, so with fresh air bending. And so we've been implementing simulation to assist the designer. The example I'm going to go through now is of this strut product. And what you can see is the simulation of the forming process. The rolls have been taken away for clarity, so you can see the profile. But what you can see here is a slot which is pierced out of the strip prior to the forming process. And you could see a significant amount of distortion on that slot as it's formed quite close to the corner radius here. Now, with simulation, we were able to speak to the customer and develop a solution which involved breaking the slot down into two smaller slots, which you can see in this simulation, which is actually showing stress this time. But geometrically, the pattern of the slots is much better with far less distortion. So first of all, we now involve our customers much closer to the front of the design process. In this particular case, we were able to show them how we believe the slot would distort. We were able to run a simulation of a solution, of an improvement, and the customer was able to then make a change to that product. And so saving us a considerable amount of time, how do we not change the slot at the end of the forming process. A few other things, looking at a cross-section now of the analysis, a few other things that we were able to improve due to simulation. Looking at some of the earlier forming stations, you can see with the top, this is the top roller on which I'm now showing, and the bottom roller and the strip in the middle. The material was lifting in the center, and so we were able to modify the profile of the top roll in the first 6 forming stations to hold the material down. Another example shows where high forming stresses appeared to be in the strip outside of the forming regions. This particular, the second roll forming pass, is actually only bending in the center of the strip, but the stress was shown on the outer flanges of the strip. So it would appear that too much forming was being done in one go. So we developed or broke down the forming into 3 stations rather than 2, added an additional forming station, and the forces in the outer elements of the strip were considerably reduced by 20%. Again, another forming issue. The corners of this particular part of the product were not particularly well formed. By identifying this in the simulation, we were able to split the bottom roll into 3 pieces and put the bottom roll on bearings and so run a much crisper and tighter form. So in conclusion, there was a change to the slot formation within the product. There were 29 tooling modifications that were made as a result of the simulation process. We were able to identify the material strip width to be reduced by 0.2 millimeters, and we redesigned 11 forming stations, and this was all before cutting any material. When the tooling was manufactured, the product was commissioned 48 hours after the product was set. There was no modifications to the tooling, and we estimate that there was a saving of at least £10,000 and quite a few weeks of development. This particular product had a grade A rating as well from our customer. So as a case study, it's a very good example of how simulation can support the designer in the roll tooling design process. I'm now going to hand over to Bas. He's going to talk you through some case studies of some other roll forming product and process applications.
Hi everybody, my name is Bak Nguyen. In this part, I'm going to present 3 typical examples of FAA application in our group. The first example is about the ultra steel dimpling process and products. The second example is about the shear cutting of the cold form steel products. And finally, the third example is about the acoustic performance of cold form steel products. So this is the first example. It's about the ultra steel dimpling process and products. My colleague, Dr. Martin Ellis, already gave you a brief introduction about the traditional cold roll forming process. As you can see again here in the slide, that is a flat strip transport through a series of rolls arranged in tandem to cold roll form the flat strip into a desired section. So the dimpling process is a process that applied priorly to the traditional cold form process. In this dimpling process, we use the pair of 2 rolls with a special desired pitch outside of the rolls that we can stretch the flat strip to apply the dimple above or below the strip to develop into the dimple strip. Then the dimple strip travel through the rolls at the traditional cold form process, and then we can develop a variety of dimple products that we saw on the right side here. This gives you on the left gives you a closer look at how the dimple shape form in a section. So by applying the dimple on the section, for the whole, the thickness and the whole section, we are applying the core work on the section, which can significantly improve the strength of the material and the end product. But we face some design challenge. This is because the complex and interrelated nonlinear change in the geometry, contact, and material properties occurs during the dimpling process. So because of that reason, there are no existing methods to calculate or design the process and product. Physical tests are limited in the sense that only some standard products can be tested, and it's also limited because it cannot give insights into the understanding of how the process and then the end products behave. So there are two greatest challenges. The first is to understand and optimize the process, and the second is how to practically represent the ultra steel products in industrial applications. So this, I'm going to give you the simulation of the ultra steel process. In this example, only a small strip is present here, and you can see on the left side is the coiled dimpling process, and on with the flat steel strip in the setup, and on the right side is the close look of the rows, the setup of the row, and also the mesh of the flat strip, plan strip. In this simulation, we use rigid body for the rows, and they form deformable bodies for the plan strip, and we use 3D elements for the to model the plan strip. We use material properties for the strip that obtained from mechanical test, in this case the tensile test, and whole of the tensile test data are applied into the simulation in terms of the tabular data. And here you can see on the left the model. The strip at the beginning, the strip is fully fixed, at one end, and the strip is then fed into the rows, and the rows rotate with an angular velocity to apply the dimple on the flat strip. When the rows grip on the strip, the fully fixed boundary condition is released, and then the dimpling process started from beginning to the end. And here show you the animation of the simulation, and you can see in the animation that the flat strip is stressed, and the dimple is applied on the strip, during the process, and the color represents the plastic strand developed in the strip during the process, from with the magnitude from minimum associated with color blue to the maximum to the associated with the yellow. So you can see the plastic strand developed in the strip during the process. If you have a closer look on the strip, you can see this is the plastic strand distribution, all around the strip, and also the mesh is represented here. So you can see a lot of plastic strand developed on the at the top of the dimple, and less plastic strand developed on around the valley of the dimple, similar to other. So this can explain of the way we apply the core work on the flat strip can increase the strength of the material by the effect of the strand hardening, as you can see here. So one way of the simulation is that we always need to validate the simulation. This is one of the first validation of the simulation is we obtain the simulation geometry on the left, and we compare with the geometry from the actual dimple strip on the right, that we measure the distance between the dimple in horizontal direction, in vertical direction, and also in diagonal direction between the two adjacent dimples. We also measure the thickness of the dimple, and then compare between the simulation and the actual process, and it come out very good agreement between them, with the difference is less than 3%. The next validation is we look at the plastic strand pattern developed in the dimple, look at through the cross section, and compare with the micro hardness test data. As you can see at the bottom of the slide, there's a relationship between the micro hardness data and the plastic strand development. If we look at here, the data can be looked at different locations to compare, but here, due to the time limit, I only show one of the locations is high 2, where we can see the plastic strand is highest at the top of the dimple, and then reduce to somewhere close to the middle, and then increase again. So this is, if we look at the test data based on the micro hardness, we can see that the hardness is highest here at the top, and then reduce, and then increase again, at the bottom. So it's very comparable result between the simulation and the test data. The other validation, and also so how good the simulation is, we perform tensile test based on the dimple strip that produced from the dimpling process presented earlier. So in this case, the dimple strip is put into the tensile test system, and we may use extensometer to measure the strength. And we set up the simulation the same, similar to the test. And then in the test, we also perform the tensile test for the plant material that all have the same material, the same coil material with the dimple strip. So if we look at the result we obtain on the left side, we can have comparison between simulation and the test. The first two curves, the red and the blue, is the result of the simulation, and the test for the plant strip. And then the green and the orange is the result for the simulation, and the test for the dimple strip. And we can see a very good correlation between the simulation and the test, with the difference, maximum difference between them is less than 4%. In this simulation, I need to remind that the all of the stress and strain data in the dimple strip is transferred from the previous dimpling process into this tensile test. And then the other validation is that we perform bending tests on the dimple strip and the plane strip, and compare with the simulation. And here you can see the test setup on the right side, and the result obtained from bending test present on the left side in terms of the loads and displacement. Again, we can see a very good agreement between the simulation for the plane strip, and also very good agreement for the dimple strip, which very much confirm our dimpling process and also our mechanical test simulation. So this is very good, because we have shown the first challenge of how to simulate the dimpling process. Through it, we can get to the understanding of the process and to be able to optimize the process. But there's remain another question that most common in application is that we have dimple products applied in many applications. How can we simulate those products? Theoretically, we can still use this approach to do that, but in order to do that, we need to develop a very large rows and also large place to perform this dimpling process. And from that, the large dimple strip developed, we can then chloroform it into section, and then from that end section, we can perform mechanical tests. Depend on the application, but that is very time-consuming, and it seems very impractical to do because it contains millions of elements, and also it's very time-consuming to transfer all the stress and strain data from the dimpling process into the products. So we propose another simplified approach in order to simulate the dimple products. Here you can see that the simplified approach is that we carry out one simulation for only one dimple, that we use 3D elements, and then from the dimple that we generate, it includes the geometry of the dimple and also the stress and strain. In this case, the plastic strain is present here, data for the dimple. And then the next step is that we will use this dimple geometry only, not the data, and then we develop the dimple strip or the end products from this generic elements, as I can show here. But we use the dimple and then generate to the dimple strip, as we can see on the right, and then we can chloroform it into section. In this example is the channel section, as I show here, using this approach, and the material properties for the dimple. In this case, we obtain from tensile test. So it means we perform separate tensile test on the dimple strip, obtain the data, and then use that data in the simulation together with the geometry that we obtain from the dimpling process. We can do it for the small products, still using the 3D solid elements like presented here. But if for many applications that we have very large dimple products, we do another simplified approach, is that we obtain the mid surface from the dimple 3D element that we create previously, and by this way we can present this mid surface as a self element, that we significantly reduce the number of elements, but still accurately present the shape, the geometry of the dimple. And then we use this generic self element to develop the large dimple strip and then chloroform it into section. On the right, you can see on the example is the the column that channel column that we create using this approach. If you have a close look, you can still see how the dimples are present in this product. That we have 1,000 of the dimple, but we are still able to do that with this approach. Another example is we can generate a very long lip channel beams. In this case, and on the right, you can have a close look on the product like this, and then this we can perform mechanical tests on these products. Another example is with the long column, but the box column, but we have irregular shape like many holes along the length of the column, but we are still able to generate such a product, and then we perform mechanical tests on those products. Here is show you an example of how we perform the cold roll forming process on the dimple strip that we generate from previous step that I present. You can see on the top is the flat dimple strip using the cell elements approach, and then this strip we go through a series of rows arranged in tandem, as you can see here. The middle one presents the strip is being formed in the middle of the process, and then in the bottom you can see the end product is a channel section. And then here show you an animation of the cold roll forming process of the this dimple strip, and you can see to see it much clearer. I took out the rows, only leave the dimple strip, so you can see it being cold roll formed into a section. And the color represents the plastic strand developed during the cold roll forming process, and then together with the products produced, we can have a look inside into the stress and strand developed in the section during the process, as you can see here. Okay, so this is the approach, but we also need to validate this approach. There's many different validation similar to the ones that I saw before, but in this example I saw one validation, but also saw one of the example of the FEA simulation performed on the channel section that we created before. This is the channel section on the left that we already formed, and then on the right is the dimple column that we perform mechanical test. In this case, the compression test of the column. As you can see, the load is applied at the top of the column, and then under compression load, the column will be buckled and fail, and we need to perform the FEA simulation for this mechanical test. And here is the simulation result. You can see at first, the color represents the displacement contour in the analysis, and you can see at the beginning the column is buckled first. Here you can see in this buckling mode, and then after this buckling we apply the load further based on this buckling mode, and then the column will fail. And this is the fail mode, and we compare this fail mode with the experimental result. As you can see on the picture on the right, the top is the simulation result, and the bottom is the experimental result. And you can see here the buckling mode compare well with the buckling mode in experiment, and then the fail mode here is also compare very well with the fail mode occurred in the real samples. If we have a closer look on the fail mode, we can see here is a very good agreement between simulation and the test. This is the displacement come in, and it correlate well to the experiment, and this the deformed displacement in the column come out, and it's also similar to the experiment result. We also look at the numbers. They are the buckling loads and the ultimate load, and the buckling loads of the simulation also also compare very well to the experimental result as well as the ultimate load, with the very small difference in a percentage between the two values. So this is again confirm the approach that we propose in this case is reliable and accurate. So now I'm going to give you a very brief presentation about the example number 2, that is shear cutting of the cold form steel products. There are many shear cutting processes in the application with different type of section that we obtain from the cold forming process. And this is one example in the shear cutting of the thick J section. As you can see here, the production model in details. If we take out the top plate of the model, you can see a bit more clear. This is, we have the J section here, and on the two sides we have the die to keep hold of the J section, and then in the middle we have the shear plate, the shear plate coming down to cut through the J section. One thing usually happen in production that we need to design the tools in order to perform this process successfully. In this case, what happened in production is the shear plate, when it cut through the J section, creates some fracture and damage that we need to understand, and we need to redesign to perform this production successfully. As you can see, during the process, because of the very thick J section, some fracture and damage developed, in the shear plate, as you can see here on the both sides, and also some at the top, at the bottom of the plate. So we perform FEA simulation for this. This is a simplified model that you can see. This is the plate. This is the dies, the two dies in yellow color, and this is the J section. This is to give you a closer look at the model. The plate will go down to cut through the J section, while the dies is fixed. At both dies are fixed. And here is the result in terms of loads and vertical displacement of the plate. You can see the loads increase to the maximum value and then going down. So what happened here is when the plate go down to cut through the J section, as you can see on the right, when it comes down to cut the J section at both sides, a lot of materials need to be cut. So you can see back on this photo the stress, very high stress developed in the plate at this position. So this that causes fracture and damage in the plate. When the plate going down further to cut most of the material at the bottom of the J section, some further high stress develop at the bottom of the plate that cause the fracture and damage in the plate. And then we can look back to what happened in the real plate and compare with the simulation, and we can see a very good correlation between them, and that gives us the understanding of how the plate fell, and from this point we can take further steps like redesign the plate or the whole system. For example, the shape of the plate or the direction of the plate that we need to optimize the process, and even the material that we may need to employ other stronger material for the plate in order to perform this process successfully. Here I show you the cutting animation of the cutting process. You can look at the process the back side of the J section, and the color represents the stress developed in the section during the process. And another to show the front side of the process, as you can see here. By using this approach, we perform simulation from variety of different sections during the cutting process. Another example to show here is with the very complicated products and the cutting process like this, as you can see. So by this, I'm moving to the last example. This is the acoustic performance of cold steel products. As you already have some information that co-form sections used widely in application, most commonly in building construction, and many of the co-form sections used in separating walls in buildings, in office, and in terms of acoustic performance, the section geometry may have an impact upon the acoustic performance of the separating walls in the system. For example, in this example, we need, based on our products, different kind of products, we need to assess if they can give benefits in terms of acoustic performance. In this case, we have two different sections. We call stud A and stud B, as you can see here. In this case, though, two studs have the same height, but different in the geometry of the flanks and the web, and also different in the flanks width. So we need to assess those two sections to see which one can give us benefits in the acoustic performance in this example. So first we perform the acoustic test. As you can see here, there's two rooms. On the left is the source room, and on the right is the receiving room. And in the source room, we have a speaker, loud speaker, to generate the acoustic pressure, and also we have microphones to measure the sound pressure in the source room, and in the receiving room we also have microphone to measure the sound pressure, and the sound pressure generated from the sound source here will travel through the separating wall, where we have the studs and the boards in the system placed in position here, and then go through the system, go to the receiving room. So the difference of sound pressure in the source room and in the receiving room will be the sound reduction that in design or in analysis that we are looking for. Here you can see that the separating walls setting up during the test. Here you can see the light, the gray color is the boards, and inside, in between the two boards, we have the stud placed in position. And in this example, we have two different studs. One is that I already mentioned. So we perform different tests, two different tests for two different studs, and then look at the sound pressure and sound reduction to see how they behave here. So this is the simulation. In this example, we perform the FEA simulation in 2D analysis. As you can see here on the bottom is the yellow color represent the short room, and this is the receiving room. and in between them is the board and the studs. If we look closer of the system of the board, we can see here, this is the stud. In this case, is the stud A that you can see. And then the pink color element here represent the air cavity in between the board, that is in blue, light blue color here. So the air cavity connect to the stud, and then also connect to the board, and connect to the receiving room and the short room that show a part of the elements here. This is show the system at the corner. As you can see again here, the stud and the air cavity connect to the stud, and we apply the south pressure on the wall of the short room, and the two circles you can see here is the area that we measure the south pressure magnitudes in the short room and in the receiving room, similar to the one set up in the test. And here to show you a bit detail about the two different studs that we use in two different acoustic analysis. This is for stud A, and this is for stud B with different shape. And here is the result represent in terms of acoustic pressure distribution for different frequencies, from small frequency to high frequency. Here you can see that the pressure distribution on the in the short room, and this is distribution in the receiving room at a frequency of 125 Hertz, and this is a higher frequency. And here's the result in terms of south pressure magnitudes represent in decibel. As you can see on the left is the result in terms of south pressure against frequencies from small frequency to high frequency at 10,000 Hertz. And for each of the stud system, we perform two tests to take into account of the variation, during the test condition. So in this example, represent the result of for the stud A. We have two test results, test in green and orange, and the simulation result is in blue color. And you can see the result for the source room between the simulation and the test are very good in agreement. And the same on the right is the result for the receiving room. And again, you can see the simulation result in blue curve is also in very good agreement with the test results. By subtracting the result, the south pressure between the source room and the receiving room, we will obtain the reduction in decibels between the two rooms. This reduction indicates the how the system perform in acoustic performance. You can see again the simulation result in blue curve agree very well with the experimental data. This is for stud A. We perform use the procedure and perform other simulation for stud B, and then we also obtain the result for stud B. Here's the result compared with the test. We use rating methods in British standards for acoustic performance to obtain the sound reduction index number. As you can see here, for the test data we obtain for stud A is number 40, and for stud B is 42 decibel. If we look at the simulation result. In the middle column here, you can see stud A we have 1041 and stud B 43, which is again correlate very well to the test data. So this helps us to understand the acoustic behavior of different kind of stud, and also give us an idea of the how much beneficial, which stud can give us from the simulation, and can help us in product and development of the different kind of studs in acoustic performance. Now, I'm going to the summaries and conclusion of my presentation. I have given the 3 typical examples of FEA application in Hartley group. The first is about the ultra-steel dimpling process and products, and the second is about the shear cutting of steel products, and the third is about the acoustic performance that I just present. Through the examples, some conclusions can be given here that in our manufacturing process and product can be simulated by Mark and Mentat, and we use test results to validate the FEA simulation, and it can be concluded that the FEA approach can be used as an alternative and complementary method to analysis and design of coiled form process and products. Thank you.